Hi friends, it's the Science Chef again. In this video, we'll be looking at pH and indicators in the fourth part of our series on acids, bases and salts. Go nowhere and we'll be right back after this break. In our last tutorial, we learned about neutralization reactions and their applications. If you'd like to learn more about the definitions and properties of acids and bases, check the link in the description. pH, which stands for potential of hydrogen ions, is defined as the negative logarithm to base 10 of the hydrogen ion concentration of a given solution, or the logarithm to base 10 of the inverse of hydrogen ion concentration of that solution. A pH scale is a scale used to measure the degree of acidity or alkalinity of a solution. It is divided into 15 major calibrations and numbered from 0 to 14, with 0 to 6 being the acidic region and 8 to 14 the alkaline region, while 7 is neutral. Within the acidic region, 0 to 2 is considered as strongly acidic, while 3 to 6 is weakly acidic. Similarly, within the alkaline region, 8 to 11 is considered as weakly alkaline, while 12 to 14 is strongly alkaline. Examples of some substances and their pH are dilute hydrochloric acid with a pH of 0.6, lime juice with a pH of 2.35, soda water or carbonated drink with a pH of 3.0, milk with a pH of 6.8, pure water with a pH of 7.0, baking soda with a pH of 8.3, milk of magnesia with a pH of 10.5, sodium carbonate solution with a pH of 11.5, lime water with a pH of 12.4, and caustic soda, that is sodium hydroxide solution, with a pH of 14. Let's now take a look at indicators. Though there are many types of indicators, our focus in this lesson shall be on acid-base or pH indicators. An acid-base indicator is an organic dye that changes color depending on the pH of the solution. It is usually a weak acid or base and can either be used as a solution or paper strip. Examples of common indicators and their colors in different media are shown on the screen. A universal indicator has a band of colors that shows the acidity or alkalinity of the solution being tested. Unlike other indicators that just indicate whether a solution is acidic or alkaline, we can use the universal indicator to find the specific pH of a solution, at least to the nearest whole number. Every acidic substance has an element of alkalinity in it, and the index used for determining the alkalinity of a substance is its potential of hydroxide ion, also known as the pOH. Just like pH, pOH is the negative logarithm to base 10 of the hydroxide ion concentration of a solution, or the logarithm to base 10 of the inverse of the hydroxide ion concentration. The relationship between the concentrations of hydrogen ions and hydroxide ions in a solution is given by the ionic product of water. That is, hydrogen ion concentration times hydroxide ion concentration equals to 10 raised to the power minus 14 mole squared per dm raised to the power 6. For a neutral solution like water, its hydrogen ions concentration equals its hydroxide ions concentration. This implies that the square of the hydrogen ion concentration equals to 10 raised to the power minus 14, and the hydrogen ion concentration equals to 10 raised to the power minus 7 moles per dm cube. This means that in a neutral solution, the hydrogen and hydroxide ions concentration equals 10 raised to the power minus 7 moles per dm cube each. From equation 5, if we take the logarithm to base 10 of both sides of the equation, we will obtain the log of the product of the hydrogen ion and hydroxide ions concentration to base 10, which equals to log 10 raised to the power minus 14 base 10. Applying the following laws of logarithm, log xy base a equals log x base a plus log y base a, log x raised to the power n base a equals n log x base a, and log a base a equals 1. To the above equation, we obtain log of hydrogen ion concentration to base 10 plus log of hydroxide ion concentration to base 10 equals to minus 14 log 10 base 10, which equals to minus 14, since log 10 base 10 is equal to 1. If we divide through by minus 1, we obtain minus log of hydrogen ion concentration to base 10 minus log of hydroxide ion concentration to base 10 equals to 14. We can rewrite the equation as minus log of hydrogen ion to base 10 plus minus log of hydroxide ion to base 10 equals to 14. But the negative log of hydrogen ion concentration to base 10 is equal to pH, and the negative log of hydroxide ion concentration to base 10 is equal to pOH. Then, substituting these parameters into the above equation, we will obtain pH plus pOH equals to 14. Equations 1 and 3 are used to determine the concentrations of hydrogen ions and hydroxide ions respectively in a solution if the pH and pOH are known, and vice versa. Equation 5 is used to determine the concentration of hydrogen ions or hydroxide ions in the solution if the concentration of one of them is known, while equation 6 gives the relationship between pH and pOH and is used to determine the pH or pOH of the solution if one of them is known. Let's now see how we can apply this formula by solving this problem. Calculate the pH and pOH of the following solutions. 1. 0.50 molar H2SO4. 2. 0.01 molar calcium hydroxide. 3. 0.125 molar HNO3. And 4. 0.002 molar sodium hydroxide. In this question, we are given the concentrations of the acids and alkalis and asked to calculate their pH and pOH. For the sulfuric acid, the first thing you are expected to do is to write the equation of dissociation of the acid. From the equation of dissociation, 1 mole of the acid dissociates to give 2 moles of hydrogen ions and 1 mole of sulfate ions. Being a diabasic acid, we will multiply the given concentration of the acid by 2 to get the total concentration of the hydrogen ions in 1 mole of the acid. Substituting this value into the pH formula and evaluating, we obtain 0 as the value of the pH. This is because the log of 1 to any base is 0. To calculate the pOH of the acid, subtract its pH from 14, and that gives us 14. For the calcium hydroxide, the dissociation of the alkali gives 1 mole of calcium ions and 2 moles of hydroxide ions. Next is to multiply the given concentration by 2 to get the total concentration of the hydroxide ions. Note that the concentration of an alkali is the amount of hydroxide ions present in 1 dm cube of its solution. The same way the concentration of an acid is the amount of hydrogen ions present in 1 dm cube of the acid's solution. After that, substitute the hydroxide ion concentration value into the pOH formula and evaluate to obtain the value of its pOH as approximately 1.7. To calculate the pH, subtract the pOH from 14 to obtain 12.3. For nitric acid, its dissociation gives us 1 mole of hydrogen ions and 1 mole of nitrate ions. Since it is a monobasic acid, we will use the concentration as given because it is equivalent to the hydrogen ions concentration. So, substituting this value into the pH formula gives us the pH of the acid as approximately 0.9. Subtracting that value from 14 gives us its pOH, which is 13.1. For the sodium hydroxide, it dissociates to produce 1 mole each of sodium and hydroxide ions. Being an alkali, its concentration is that of its hydroxide ions in solution. So substituting this value into the pOH formula and evaluating, we obtain approximately 2.7 as the pOH. To obtain the pH, we subtract the pOH from 14, and that gives us 11.3. From our solutions, we would observe that the lower the concentration of the acid or alkali, or the more dilute a solution is, the more its pH tends towards 7. In our next tutorial, we'll be dealing on how to calculate the pOH of a titration mixture and how to calculate the hydrogen and hydroxide ions concentrations when you are given the pH. Subscribe to our channel and turn on your notification bell to get notified when we publish the video. Until then, remain on top.